Hi there, this is Magnetism, lesson 2, and this is the F equals BQV. So let's start off with this recap question from last lesson. If you want to pause and have a go. A horizontal copper wire of mass 4 times 10 to the minus 3 kilograms and length 80 millimeters is placed perpendicular to a horizontal magnetic field of flux density 0.16 Tesla. The magnetic force acting on the wire supports the weight of the wire. How many electrons are passing a point in the wire each second? So, how many electrons passing a point in the wire in each second is the current. So we can use F equals BIL to find the current. And the current per second is the charge. And then we know the charge of an electron. So let's start off by finding the current. So F equals BIL. It's a way of remembering it. BIL. Rearrange to find I. So I is equal to F over BL. And the force is the weight, so that's the mass, 4 times 10 to the minus 3. Multiplied by gravitational field strength, 9.81. Divided by B, which is the magnetic flux density, 0.16. Multiplied by the length of 80 millimeters, so 80 times 10 to the minus 3. And that gives a current value of 3.07 amps. Then we just need to finish this off. So we've got 3.07 amps, and 3.07 amps is 3.07 coulombs per second. So in 1 second, we've got 3.07 coulombs. So if we divide by the charge of an electron, which we should know by now is 1.6 times 10 to the minus 19 coulombs, that will give us the total number of electrons that make up the 3.07 coulombs of charge. And that is 1.92 times 10 to the 19 electrons. Okay, let's move on. Some notes. Charge deflection by a magnetic field. So this is from GCSE essentially. So electric charges are deflected by magnetic fields provided they are not travelling parallel to the field lines. That's important. If they're travelling parallel to the field lines, they experience no force. That links back to the left-hand rule. If you remember, the thumb for the motion, the first finger for the field, and the second finger for the current are all perpendicular to each other. There must be some form of perpendicular component to the direction of the magnetic field for a force to be experienced. So basically, positive and negative charges are deflected in opposite directions. And we'll look at this in more detail soon. So what happens when a charged particle enters a magnetic field? Well, when a charged particle enters a magnetic field, it experiences a force at a right angle to its motion. So let's say a proton entered a magnetic field. It would experience a force, so experience a force at a right angle to its motion. And that's at all times. That's important because if you experience the force at a right angle to your motion, you'd start to turn in a circle. Start off on a parabolic path, but then as you were turning, you keep experiencing a force at a right angle to your motion. So that would cause you to turn, and you'd turn into a circle, and you would exhibit circular motion. Okay, let's move on then. So a force and a charge moving in a magnetic field. So I'm just going to give you the equation. So for the current carrying conductor, it's BIL. However, we can see that current is charge over time. And we can substitute that in. So what we end up with is F equals BQL over T. And length over time is velocity or speed. Therefore, that gives us F equals BQV. Force measured in newtons, B is the magnetic flux density, charge measured in coulombs, velocity meters per second. So we can write these down. So forces in newtons, magnetic flux density is Tesla or Weber per meter square. Q's charge in coulombs, velocity is obviously meters per second. Let's move on then. Remember to pause or rewind at any time if you need to. So let's do this one first of all. Very simple. Calculate the magnitude of the force acting on an electron travelling at 3 times 10 to the 4 meters per second, normal to a magnetic field of flux density 1.7 Tesla. Charge on the electrons given, but we should already know that at this point. So simply F equals BQV. So B 1.7, that is a very strong magnetic field, by the way. Remember the ones at hospitals for MRI scanners around 0.5 Tesla to 1 Tesla. So 1.7 is huge. Times the charge, which is 1.6 times 10 to the minus 19. Multiplied by the velocity, which is 3 times 10 to the 4. If we calculate that, we get 8.16 times 10 to the minus 15 newtons. So look at the next one. So you're going to think about this one. So there's a hint in there. You're going to pause and have a go. It says derive an equation to show the frequency of rotation of a charged particle as it enters a magnetic field. So we've got the equation to describe the force on a charged particle as it enters a magnetic field, which would be BQV. And the hint, circular motion. So we can make that equal to mv squared over r, which is for the centripetal acceleration of an object turning in a circle or exhibiting circular motion. Then what we can do is cancel these and rearrange to find v. So v is equal to BQR over m. Then we need velocity in a circle. So there's one equation that you should know. That is velocity is 2 pi r over t. But this one wants frequency. So frequency is 1 over t. So velocity is also 2 pi rf. Then what we can do is combine these two equations. So we're going to BQR over m equals 2 pi rf. The r's cancel. And we're left with frequency. So frequency is BQ divided by 2 pi m. And that's known as the cyclotron frequency. You can be asked to do this in examinations and then use it to make calculations. So let's do so. So I'll make sure this is, if you got this right, well done of course. If not, make sure it's down. You might want to retry this one and then we'll move on. So let's pause and answer this one as well. A proton enters a B field of magnitude 3 Weber per meter square. Calculate the frequency of rotation and the time taken for 10 revolutions. So frequency of rotation, we can just use the equation BQ divided by 2 pi m. The charge and the mass we've used, and it's on the data sheet. for any relevant exam board. Constants like this at this point in time though, probably should know. So let's put the values in. So B is 3 multiplied by the charge. So the charge of a proton is the same as an electron, 1.6 times 10 to the minus 19 coulombs, divided by 2 pi multiplied by the mass of a proton, which is on the data sheet, 1.67 times 10 to the minus 27. So that gives the frequency, and the frequency is 4.6 times 10 to the 6 hertz. So that means there will be 4.6 times 10 to the 6 revolutions per second. Then obviously time period, so time taken for 10 revolutions. Time period is 1 over f, so if you've got that full number in your calculator, time period is 1 over f, so 1 divided by 4.6 times 10 to the 6, and it's asking for 10 revolutions, so just times that number by 10. And if you use the full number, you should get 2.19 times 10 to the minus 7 seconds. Hopefully that went okay. So let's have a look at what's next. So a bit of a tricky one. So let's pause and have a go. For the first one, as a tip, you'll need to use Fleming's left-hand rule. And then I'll take you through the answer. So we've got a doubly charged copper ion, which means it has 2 times the charge of an electron, entering a uniform B field at a right angle to its direction. So we've got the mass of the copper ion, we've got B field strength and the speed. But the first question says, which direction will the ion initially travel? So you can use the left-hand rule. So if you point your middle finger, which is the current and the direction that the ion is traveling, because current is positive to negative, and then the uniform B field is moving up, so your first finger will point up. Your thumb will point out of the page or out of the plane of the diagram or out of your phone or your screen. So which direction will the ion initially travel? We could simply say out of plane of diagram, or out the page, or words to that effect. Hopefully that went okay. So next one, calculate the radius of curvature of the path the ion will take. So we could say BQV equals mv squared over r. Cancel the v's. And then rearrange to find r. So r would be mv over bq. And then we simply need to put our values in. So I'll do that now. So the mass is 1.0552061. If you didn't use the full number, doesn't really matter. Times 10 to the minus 25. Times the velocity, 7.2 times 10 to the 5. Divided by BQ, so 0.38. Multiplied by the charge. Now it's a doubly charged ion, so that would be 2 times the charge of an electron. So that would be 3.2 times 10 to the minus 19 coulombs. So that gives a radius of curvature. Put that down here, which is equal to 0.62 meters. Hopefully that's okay. Write the full number down. So let's clear the screen and then answer part B. So the charge is replaced with a single positively charged copper ion instead of a double. So the equation which we got was R equals mv over bq. So if we half the charge, we get double the radius. So we need to do the 0.62 times 2. And the 0.62 times 2 is 1.24, but if you use the full number, you would actually get 1.25 meters. So if you've got 1.25 or 1.24, that's fine. You should really be using the full number, but it's okay in this instance. And then the next one, if the strength of the magnetic field is doubled. So if we actually doubled the strength of the magnetic field, the radius would do the opposite, it would halve. So that would be the original 0.62 meters divided by 2. And the 0.62, the original, divided by 2, would give us 0.31 meters. So hopefully that all went okay and you've learnt something. Thanks for watching. And I'll see you for lesson 3. Take care.